Hey, doing everybody. Like I said, I want to go over some of the stuff that we worked through in that little activity. So I have a couple things already prepped over here, just to go over some of the things we saw. So here is a piece of T tape. Here is, messing it up, a piece of B tape. And if we do this right, we'll definitely see that those two are attracted to each other. There's this attractive force. Now if I keep, let's see, a T and grab the other T that I made, hopefully stuck to my table, we'll see these guys, yeah, repel each other. We could definitely see that they don't want to go near each other. And then you were supposed to you're supposed to test other objects, like a piece of paper and a piece of aluminum foil. So we're just going to go through some of those results you should have seen. Now, you may also be able to tell, I'm going to stand up. No, I'm going to sit down. You may also be able to tell I'm a little bored, so I have some terrible sound effects in this. The lab, blah, blah, blah. All right, so we're going to discuss. Remember, when you do your own PowerPoints, don't put any of this animation stuff in. So we were looking at the charge of sticky tape, the behavior that was displayed. So we should have always seen it either attract or repel or nothing. Like if I put two pieces of paper near each other, we wouldn't see anything happen. What makes you believe the objects were charged? Hopefully we know the objects are charged if there's an attraction or a repulsion, but we're going to have to talk about that. All right. So no charge we know means neutral. Now neutral doesn't mean they don't have any charges on them. Neutral means, as you should know, that we have the same number of positive and negative charges on them. So the behavior displayed that makes you believe those objects were not charged, if the behavior that shows they're not charged is if I hang two things near each other, again, two pieces of paper and I bring them near each other, absolutely nothing happens. But when I brought a T and a B near each other, or near the, stuck on me, still stuck on me, we should have seen something happen. Actually, there's a little bit of an attraction there. And we saw the same thing with the other one, I hope. We'll get into that. So if the paper and the foil were neutral, how can you explain their attraction to both positive and negative objects? What does neutral really mean? What does no charge mean? Equal amounts of positive and negative charge. Neutral means kind of all of those things. This no charge isn't really good. It should say no net charge. Remember, net means total. And how can we explain that things were attracted to the paper and to the foil? Well, it seems that no matter what the charge is. Now, this whole activity goes through and never really talks about positive and negatives. We know positive and negative. And no matter what the charge is, every charged object is attracted to any neutral object. And that's something we talked about in class. Now, when the tapes became charged, they became charged because as I stuck them together and then I ripped them apart, really that sticky tape is really just kind of friction. So when I was ripping those things apart, we were transferring charge. Remember, there are three different ways to charge objects. One of them is friction, and that's how we're charging the tape. So it started as a net charge of 0, the same number of positives and negatives, and there's a picture of this later on. Then as I ripped them apart, some negatives moved to one piece of tape, leaving only positives on the other. So we were transferring these subatomic particles. The reason I have that is because people think subatomic means something crazy. No, an atom is an atomic level. Atoms are made up of, protons and electrons. So we're moving electrons, which aren't atoms, they're just part of the atoms, or subatomic particles. So yes, you were studying subatomic physics. How kind of cool is that? This just goes through that whole thing again. Sorry, this is kind of repetitive. Based on our observations, we can assign that we transferred some small object. Again, those small objects are electrons. Remember, the size of an electron is 9.11 times 10 to the negative 31 kilograms. So that is 0.9 with 30 zeros before it. 0.00000, 30 of those, and then a 9 kilograms. Now, when the charge is moved And we don't know how to figure this out just yet. We'll be able to figure that out, though. When the charge is moved, we know, well, I know, that we are assigning a positive and a negative. We're going to assign the tapes to be one positive and one negative, and the way our experiment works, the tape that's on top ends up positively charged, and the bottom ends up to be negatively charged. And we can set that up with different experiments. I mentioned in class something that's called the triboelectric series, something we don't need to really look up, but some objects are better electron donors, some are better electron receivers. So I could charge an object negatively. I was looking for something to do that here with, but I don't have a balloon. Balloons are easy to charge negative, and then if I bring a T-tape near the balloon, it'll attract, and a B-tape near the balloon, it'll repel. And we know that the opposite charges attract and the like charges repel. So our possibilities, how we can figure this out, is either one of those acquires positive things, one of those acquires negative things, and we know positive things aren't allowed to move. So we know that negative things transfer from one object to the other. Or in this case, since they start together and we're saying that the T-tape was positive, that means the bottom rips away the negatives. This kind of summarizes all of our stuff. Then we're going to get into the older version of the model. We know we're moving things that are smaller than atoms, subatomic particles called electrons. Those things are mobile. We're allowed to charge objects, and we charge objects by either adding or removing electrons. Now, if you want to look at this website, this has some information about the J.J. Thomson model. That's the plum pudding model. Remember, we know that's not a real model, but it makes this much easier to deal with. And the idea of transferring electrons was something that J.J. Thomson thought was okay. I definitely recommend looking at this website a little bit. So we know he came up with this model that's called the plum pudding model, in which he thought these little red dots were the plums, were negative things, and this whole blue was just a positive for a net charge of 0. So now here we have our plum pudding model. Again, it's not the correct model, just makes it easier. When we stick them together, here we have the top tape and the bottom tape. We stick them together, the electrons are allowed to move around, and we know that even still today. But now when I ripped them apart, some of them ended up, the extra electrons ended up on the bottom, so that's negative. The top tape lost some electrons. Notice not all of them, but some electrons, and that is the positive tape. Now again, this is allowed to happen in real life today, just not in this plum pudding model. That is what we believe not to be true. Now, a neutral object is allowed to move those electrons around, right? So this was like the balloon to the wall. The reason why every neutral object will attract any charged object is, let's say I have this big positive charge here. We'll see all these little what's it called? Dots, those electrons, those plums. Those would be attracted to this positive thing. Now, I couldn't manipulate this image, so what I did is I took a negative and just put it on the other side, and the same thing would happen. This negative would push all of those negatives away, leaving a positive side. This was called charging by induction, and this was influencing charge. Notice the net charge always stays the same, but it's got a negative side and a positive side. So these are two different images. On this image, all of those negative things are attracted to that positive. In this image, all the positive side would be attracted to the negative, because every neutral object will attract any charged object. So now this last question, this is where we're going to start moving into. Why is the foil more attracted than the paper? Hopefully you saw that. And what do we know about metal, specifically with electricity? Now this is going to be talking about insulators and conductors. The next thing we do is actually going to be Coulomb's law to calculate some forces. But conductors gets into current electricity, or something that's more fun, moving electricity. I've got 10 seconds to keep this under 10 minutes, which is what I wanted to do. So stay charged, everybody. and to watch us as many times as you want.